Okay, everybody, welcome to the lesson on resonance in dampening devices. Okay, so we're just going to talk about something called natural frequency. They already know that most objects like to vibrate at a certain frequency. So, for example, if you look at these different pendulums, you'll notice that the pendulums have different lengths, and each of these will vibrate slightly differently. Well, each one is said to have a natural resonant or frequency, an object at which it likes to vibrate. And you can see here that we've got pendulum A and E have the same length, so they probably have the same frequency. And so do B and D. They have the same length, so they must have the same natural frequency as well. C is on its own. Does not have the same natural frequency. It does have one, but doesn't match the other objects. Now, almost any object has a natural frequency. You have a swing, a glass, structures like bridges or buildings. And you got to be careful when you're designing structures that you don't want to have unnecessary vibration because of this natural frequency. You don't want buildings and bridges to sway, for example. So something that to keep in mind is what we call resonance. This is when we have two objects and somehow they're interconnected. It could be through the air, it could be through the string directly, but somehow they're interconnected and they happen to have the same natural resonant frequency. And what happens is, in the case below down here, when the objects have the same natural frequency, when one of them vibrates, it can transfer objects through the medium to the second object, causing the second object with the same frequency to vibrate. And it gradually does so. And basically, this is a very, very gradual process, and eventually you have a big change in amplitude. So think of a swing. Okay, you saw there how gradually pushing the guy in the swing, bit by bit by bit, the swing amplitude increased until it got to the point it was quite high. So it's a gradual increase in this transfer of energy, the amplitude. We can also have this occurring in physical objects. For example, a wine glass. Let's take a look at this video.
When struck, a wine glass rings at its natural frequency. By subjecting the glass to high amplitude sound waves of the same frequency, the glass vibrates. The sound waves reinforce the vibrations, continually adding energy to the glass. This is resonance. Eventually, the amplitude of the vibrations becomes stronger than the glass can withstand, and it drops.
Again, the key thing to remember here is the speaker and the glass had the same natural frequency. And what happened was the energy from the speaker transferred through the air into the glass and caused the glass to vibrate at that particular frequency, bit by bit. And you saw there was a dramatic increase in the amplitude until the glass shattered. Here's another interesting example. This is the turbo train. This is a fantastic train developed by the Canadian government in the late 60s, early 70s. It was based on a turbo engine. It was the first turbo engine that was placed on trains. And it was the first high-speed rail train that was developed in North America. It even had a tilting body system. So it was very, very advanced for its time. Unfortunately for me, at the time we lived near a railway track. And what would happen is most trains went by, not a big deal. But when the turbo train went by, we noticed that one of the bedroom windows began to vibrate. So what would happen is as the turbo train was vibrating, the engine vibrate, that vibration transferred to the window because they happened to have the same natural resonant frequency. And the window began to vibrate at that particular frequency. So needless to say, we're kind of scared to go near that window until this turbo train was put out of commission. The same phenomenon can occur with bridges as well. So one of the most famous examples is this. This is the Tacoma Narrows Bridge in Washington. You can see here how the bridge is vibrating back and forth. Oops. Let me go back a little bit. And the bridge is vibrating back and forth. There we go. And it's a torsional vibration. What happened is little vortices of winds went underneath the bridge, pushing and pulling on the bridge underneath the deck. And this gradually caused an increase in this torsional vibration that ultimately led to the failure of the bridge. It crashed. And they rebuilt the bridge much, much stronger as a result. Other examples of bridges would be this one here. It's the Millennium Bridge in London. It's a pedestrian bridge we'll be looking at. And there are other examples of bridges in history that have collapsed because of soldiers marching across them. When they're marching across, they're all marching with the same frequency. If the frequency of the footsteps matches the frequency of the bridge, you can have a transfer of energy to the bridge and the bridge could collapse. So here's a warning sign on the Albert Bridge in London. It's asking soldiers to go out a step to prevent resonance from occurring. Is that here we have the Millennium Bridge.
The bridge opened on the 10th of June, 2000.
Oh, not very good video. Let me just very quickly switch to this site here. Now, in this particular bridge, as on opening days, as individuals are walking across the bridge, something interesting happened.
The bridge opened on the 10th of June, 2000, attracting thousands of people and the media. But as the people poured over the bridge, it was clear something was wrong.
So what happened here is as people are walking across the bridge, their natural swaying motion as they're walking was transferred to the bridge. And then when they realized this, they tried to, to compensate for this, they tried to shift their weight the opposite way. Well, this just further reinforced the vibration, and we had a large back and forth vibration occurring. So what ended up happening is they redesigned the bottom portions of the bridge with shock absorbers and special damping materials we'll be talking about later that absorbed this energy and prevented resonance from occurring. So quite interesting in that way. Now, these are all examples of resonance that can cause issues. We can actually have desired resonance. This is when you want to have resonance. For example, you have a child on a swing, or pushing somebody out of a snow, you rock the car back and forth and gradually build up an amplitude, and then the car can hopefully get out of the snowbank. If you're on a swing, the person pushing, their pushing frequency should match the frequency of the swing. So their amplitude's increasing. And another useful example, something called lithotripsy. Now, lithotripsy is a method of treating kidney stones. Kidney stones are typically treated with surgery. In this technique, you can use resonance to treat the stones instead. It's much more beneficial.
Patients come out, they're just in a wheelchair. They're not having to be heavily sedated or as if they were having to go to the operating room as in the past. There's no surgery, nothing invasive. Patients are wheeled out here in a wheelchair, given a light pre-medication inside. They come out here, they just lay on the table, either supine or on their belly. Use the X-ray camera here to get the stones on target. We're using real-time fluoroscopy back here to put the stones on targets. Literally put the stones that are set across here on the TV screen, so it's very much like playing a video game. The part that breaks the stone is this shock wave back here. The shock wave back here, it's a water-filled bag. This slides over into this hole in the table up against the patient's backside, and the shock waves are transmitted through the water, through the patient's body, and to the stone to break the stone. Patients are given mild sedation while they're out here. It's not heavy sedation, so there's much less risk involved than what would be going on in the operating room. So it's much more patient-friendly and user-friendly from the standpoint of the old ways of getting kidney stones out.
So again, an interesting example of how we can have resonance occurring, and we want it to occur to help treat certain conditions. Okay, now we saw examples where we have resonance occurring because of this transfer of energy between objects. Well, sometimes we don't want this to occur, and we want to prevent vibration. So we have something called damping. And damping is where we take a vibration and reduce the vibration using a variety of mechanisms. Some of the things that we can do are we can use these special absorbing materials. Now, these materials can absorb the energy of a vibration. So here's a great example of energy absorbent materials in a practical situation. You can see here we've got some kind of CD player, and as it's spinning, it's creating vibrations, and you see those vibrations being transmitted to this little glass of water. Meanwhile, on the other side, you can see there's a glass that's on top of the special energy absorbing materials, damping material, that's not even moving a little bit. So again, lots of practical applications of this. Okay, now getting back to the video. Now sometimes what happens is, instead of using sound absorbing materials, we can use things like shock absorbers. And shock absorbers can absorb energy using mechanical springs or other types of devices. Okay, so here's an example of that. So this is damping control for trucks. It's developed by MAN Truck Systems in Europe.
Switching lane to road safety. And rear axles. King pressure, load status, accelerator position.
So these are a variety of sensors and active shock absorbers to help prevent the motion of the truck you'll see in a minute.
Vehicle speed. All values are analyzed by the system control unit. The suspension firmness required for each situation is then set by means of an electromagnetic valve on the shock absorber. CDC ensures that the roll angle is greatly reduced under comparable driving conditions, allowing more reliable mastery of the vehicle.
So you can see here what a dramatic difference having this damping control mechanism makes in the control of a truck and other large vehicles. So again, example of damping. So basically what you want to do is you want to make sure that you go through your textbook, look over information on resonance, look over information on damping, and answer any of those associated questions. A copy of this PowerPoint has been placed in the folder, in the roster on your school computers for you to use. The videos are there as well. Take care. Bye.